Hi, my name is Erin Jeffries, and I'm going to be talking about the processes of celiac disease and how nanodiscs may be able to help alleviate the problem. First off, I want to explain what a celiac patient's stomach looks like. It all starts off with gluten, which is first digested into gliadin and glutenin. Sadly, these are not fully digested, and in someone with celiac, they often won't be because of the prolamins associated with them, thus the immune response. Here shown is a drawing of the enterocytes. These are the cells on the surface of the villi and small intestine. In a celiac stomach, gliadin, which is an undigested gluten, will lodge itself in enterocytes. The enterocytes will recognize this buildup and will trigger an immune response, as to say, hey, something's here that should not be. This causes zonulin, in purple, to be released, which loosens the tight junctions, in pink, between enterocytes, thus allowing more undigested gluten through. This passage through the cell wall triggers transglutamase, or TTG, to be released. This is the teal rhombus. TTG binds to the undigested gluten and changes their structure to a position the immune system has recognized as a threat, noted as a green square. This sets off the primary immune system response. Antigen-producing immune cells, the yellow star, pick up the changed gluten and present it to the T cells, noted in gray. The helper T cells identify the gluten in the enterocytes and attack them, first by releasing toxic secretions that directly hurt the enterocytes, then by signaling the killer T cells, noted in blue, to directly attack the enterocytes, and finally by signaling mature B cells in red to make two antibodies, one that attaches to gluten fragments, the triangle, and one that attaches to TTG, the plus sign. This causes severe damage to the enterocytes, which are crucial to many functions of the small intestine. Now, I understand this process is specific and tedious, and as with many autoimmune diseases, our understanding of how each process works changes every day. This means new solutions are always on the rise. The first, most well-known, and only approved treatment for this disease is a gluten-free diet. This completely eliminates the introduction of any type of gluten cells in the intestines and means that the immune system is never triggered in the small intestine. When interviewing a family member who has had celiac disease for 46 years and was only diagnosed 11 years ago, he talked about his struggles with the gluten-free diet. Celiac disease was not well known until recently, and gluten-free food has only lately been popularized. Due to this, he explained how convenience and scarcity were and still are his biggest problem. Lack of restaurants serving gluten-free food that hadn't been contaminated to any extent, the difference in taste and texture of foods without the structural protein, and how expensive many gluten-free options are, all contributed to his dislike of the gluten-free diet. However, due to this being the only available treatment and the obvious relief of gastrointestinal symptoms he experienced when eating gluten-free, it is hard to rationalize straying from the diet. Many of the solutions that are being worked on try to stop the process on the front end, meaning undigested gluten never gets to the small intestine. Enzyme supplementation and protein degradation is a prime example of this because the focus is finding enzymes that can break down the hard-to-digest prolamins. The problem with this solution is you would need to take these pills every time you had gluten, and mostly in high quantities to see a difference. Genetically modifying the gluten would allow the gluten to pass without being recognized by your immune system, and therefore would not be attacked. This seems to be a viable strategy but needs more research to see how consistent it is and has the controversial public opinion aspect on genetically modified foods. Polyphenols, I believe, is the most diverse and the most recent. There are many types of polyphenols, so they can attack the problem on many different fronts. There has been widespread research on these in similar autoimmune diseases, but because it is so new, not much research has been done on celiac disease specifically. With these previous treatments and research on these biopathways, I thought that nanodiscs may be a new angle to look at this problem from. Nanodiscs are able to mimic a cell membrane. They are currently used for research on membrane proteins. Membrane proteins help to recognize molecules such as immune molecules called chemokines and trigger an appropriate immune response. The property of these nanodiscs that could translate to celiac disease is the ability to encapsulate proteins and reassemble it into a small disc of lipid bilayer surrounded by membrane scaffolding proteins. SMA, or styrene malic acid copolymer, is one approach used to cut out the lipid bilayer into discs that can be extracted while retaining the lipid bilayer but are small, stable, and water-soluble. There are other approaches to remove the membrane proteins that have differing effects in each area. The goal of nanodiscs would be to find a way to adapt the techniques used in membrane protein research to encapsulate the undigested gluten proteins to either allow safe passage through the small intestine without immune response or to stop the gliadin from permeating the enterocytes.